Black holes. Well, you know what fascinates me the most about this universe? It's its mysteries. It's filled with mysteries. And black holes are one of the biggest mysteries of the universe. Sit tightly, because this episode is gonna get longer, and well, it's gonna give you some head spins, because we're gonna talk about black holes, and so we're gonna go deeper into that thing, like black hole deeper, I think. So the gravity of this video will get really strong. Stay with me. What is a black hole? It's a region in space where the gravitational field is so strong that the escape velocity of that region exceeds the speed of light. In other words, you need to travel faster than the speed of light to escape from the grasp of it, which being impossible, nothing, even light, can escape from the black hole. No light reaches to your eyes from the black hole. It appears to be black. Now, a hole, well, it's because of its enormous mass. Actually, it bends space and time to an extent that the space-time curvature becomes infinite. I know that's so bizarre to think about, but that's what happens. In theory, any neutron star whose mass exceeds 3.2 solar masses collapses onto itself, creating a black hole. But it's not the only thing. What's more interesting is that anything can be turned into a black hole. Well, the sun, the moon, the earth, or even you can be turned into a black hole. Every object has a radius called Schwarzschild radius, which, if squeezed into that radius, that object can be turned into a black hole. So let's do an experiment with gravity and, well, that Schwarzschild radius I was talking about. For this we need a computer actually. So as I said, nothing can escape a black hole, not even a light, so how can we see it, right? No, we can't actually. If nothing's gonna rotate around it, we really can't see it. But what if something circles around that black hole? Is there any chance of us seeing that black hole? What do you think? No, we can't. We still can't see that, because nothing can escape from a black hole. So whatever is lost forever. Well, I'm not getting into the Hawking radiation for now, so whatever. So as I said, we cannot really see a black hole, but we can see the shadow of its event horizon. That's possible. What's an event horizon? Well, it's a point of no return. Spooky, right? Boundary, which if something crosses, there's no way for it to come back from that region, so it's lost. And well, for decades there have been debates over the existence of black hole, and they're so strange that even Einstein said once that we should ignore them. I mean, we shouldn't really think about these strange objects because they're really so strange and weird to think about. So that's why we shouldn't really waste our time thinking about these things. He thought that once. We actually didn't have any direct proof that we can say that it's a black hole or something like that, but we observed some effects from the black hole's intense gravitational pull or intense gravitational field. We can observe the other stars that were circling around an invisible object, well, and the only explanation for those were that black hole thing. So that's how we knew that there was something else out there, but we were not really sure that was black hole, or maybe it was black hole, but we didn't have any proof actually because we cannot see it. So well, yeah, all those pictures we saw before, those all were like illustrations, artists' concepts, and well, some computer simulations and blah blah things. And we didn't really observe a black hole in real picture until now. A team of 200 scientists in 20 different countries using 8 different telescopes. Well, a network of telescopes to be exact. It's called Event Horizon Telescope, which is not one telescope at all. It's just 8 telescopes work as one telescope, which is really great. Now it's a network. It wasn't connected at all. These telescopes were not connected at any point, so it's a different thing. But they captured the first ever image of a black hole, well, a shadow to be exact, for the first time. Now just think about it, which was long being impossible is now possible. How cool is that? Just think, whoa, just amazing, right? It's cool, it's amazing. They captured the first ever image of a black hole at the center of Messier 87, which is like 55 million light years away from Earth in the Virgo cluster. Great, isn't it? Just amazing. Just think about it. For being able to take the picture of the black hole, the size of the telescope needed to be the size of the planet Earth, well, which is ridiculous to think about, right? Just think about it. A telescope with the size of the planet Earth, how can this be possible? But these clever people came up with an idea. They used a technique called very long baseline interferometry. Using 8 telescopes, they created the, well, Earth-sized virtual telescope. That That was just crazy. Think about it, just crazy. It's insane. It's insane. Seeing the black hole was really a hard thing to do, because it was like taking a picture of a donut lying on the lunar surface. And just think about it, a donut on a lunar surface, then just how much magnification you would require and how much resolution you require to create an image on which you can just see that donut clearly, right? So just what they did, they needed to capture, they knew that they needed to capture, collect as much light as they can, hence they felt for the need of an Earth-sized telescope. That was the reason. They needed to capture as much light they can get from that black hole. And then there were problems like weather, the atmospheric turbulences, the water vapor, so on. So many problems. So they chose dry places to capture these images. They knew that the Messier 87 galaxy has a supermassive black hole inside of it, and well, there were matters swirling all around that black hole. Now, in order to see that black hole, they needed to see through those blob of gas. Now, so they had to come up with this idea that they needed a wavelength that can get through that barrier of the gas, and which can be observed here with these telescopes. So as turned out, it was radio waves that checks this criteria. So yeah, the image was made using radio waves. There was one thing more they needed to do. They had to take the picture of the black hole by those 8 telescopes all at once, like at the same time. So, and those telescopes were not really connected with each other. So how they did it? Well, they used atomic clocks to sync those telescopes, those data, and giving it a time signature or something like that. So just so they had to do that. Now these atomic clocks actually lose 1 second in like 100 million years. That's how much accurate they are. Now, before showing this picture and analyzing it, let me talk about, well, relativity and how it predicts how a black hole should look like. And well, if the prediction matches the result, then we can say that, well, Einstein proved to be correct once again. Okay, so as the matter falls into the black hole, it creates a disk. It's called accretion disk. Now, well, because of the intense gravity of the black hole, it swirls all around it at near the speed of light. Just think about it, near the speed of light. And because of that, it actually gets excited and it emits light. But this accretion disk doesn't extend all the way to the event horizon, because there is an innermost stable orbit for matter. Now, if something crosses this limit, it falls into the event horizon. That's why it doesn't extend all the way up to the event horizon. But for light, it gets interesting, as they don't have any mass, they don't have mass. Well, they can orbit around a black hole at 1.5 Schwarzschild radii. I'm talking about Schwarzschild black holes for simplicity. But just know that all the black holes that we found are Kerr black holes. That means they are rotating black holes. So for Kerr black holes, actually this radii resembles the argosphere. I don't want to talk about those things. Those are kind of complex things, and I'm not going to talk about those now here. So if somehow you can, well, you really cannot just think that you can, I mean, you really cannot just, it's not possible at all, but still, just think, okay, just a thought experiment. So just think that you're standing there, I mean, that place where photons circles the black hole at 1.5 Schwarzschild radii, you're standing there. Now what you will see the back of your head in front of you. Now let me explain what is happening here. Your light from the back of your head is swirling all around that black hole and reaching to your eyes. That's why you can see the back of your head. It's quite interesting, I know, whatever. So this sphere is called a photon sphere, which is not really stable. Well, they're not stable because, well, maintaining this orbit, actually they cannot maintain this for a long time. They either fall into the black hole or they just get to the infinity, leaving the black hole. That's what happens. So what you are watching here, are you looking at the event horizon or photon sphere or accretion disk, or what really we are looking at? Well, get ready to spin your head, as it's gonna get a lot complicated. Well, as said earlier, black hole warps space and time, thus bending the path of light rays. Now, they travel so much of a curved path that even you can see the back of accretion disk in front. Well, let me explain, okay? Let me explain. Think of it like parallel light rays are coming towards a black hole. Now, because of gravity, some of them will fall into the event horizon, and the others will get so much bent by the curvature of space-time that some might come back towards you, traveling all around it. As parallel light rays travel, some of them might come from just above the event horizon. Now they too will get sucked up. Light rays coming in the same distance as a photon sphere will also bend up and end up inside of a black hole. Sad. It's until light rays come in 2.6 Schwarzschild radii away from it will make a closest approach to the photon sphere and will go off to infinity. Hence we get a shadow 2.6 times larger than the event horizon. So the shadow we get is the shadow of event horizon along with the backside of event horizon too. And well, because the light that comes from in front and swirls all around it and get absorbed in the front, well, we get to see another event horizon image mapped onto that shadow, and well, another one and so many, like infinite number of event horizon images are getting mapped up on that shadow. So what we will get a shadow. As we approach to the end of that shadow, you will get to see infinite number of images of that event horizon mapped onto that shadow as annular rings. This is what it would look like if you observe it being perpendicular to the accretion disk. But with this M87, it's not the case. It's not the case at all, as we will be looking at it at an angle. The whole backside of the accretion disk, which is behind, the light from that will get bent and end up in our telescopes, creating an image like this. And also the other side will also appear to be like this. And here you have it, a theoretical model of a black hole predicted by Einstein's field equations. Ladies and gentlemen, let me present to you the first ever image of a black hole. Once more, Einstein got correct. And the first thing that will come inside of your head about this image is that this image is really blurry. Well, which is obvious because you're watching something else which is located like 55 million light years away from us, and we are just magnifying it at this size. Well, just think about it. And there were so many obstacles, as I said, so many things, and we're using radio waves also, so lots of things. After that also we got this result. That's amazing. I mean, just think about it. We just saw something which we thought for a long time was not really possible to see. So it's really, really significant, and whether it's blurry or not, it really shouldn't matter that much. Now, the second thing, you will say that the color, you might think that this is the exact color of a black hole. Well, not actually. It's not the exact color of the image. They used radio waves, okay? It's just because they like this color, that's why they use this color. That's it. As they're radio waves and don't fall into the optical light spectrum, we cannot tell which color was it in real, but scientists are really proposing that the exact color may be somewhat bluish or reddish. Now let's look at this dark circle. What you're watching, what you're not watching, is forever removed from this universe. Holy cow, that's the shadow of no return land, exit portal from our universe. Well, maybe for the first time we are looking at event horizon. Well, the shadow, to be exact. We know that there's a real event horizon, not a naked singularity, which is so weird to think about. Ugh. Now let's look at this light ring. It's bright in it because the matter is being torn into atoms and reaching a temperature of billions of degrees C. It's brighter at the bottom, meaning the side is coming towards us. The light isn't coming from the sides, but coming from all the directions. And this is the accretion disk. And what we can say by this image, well, the black hole spins clockwise, judging by the relativistic beaming and whatever. So, you know, the resolution of this telescope, event horizon telescope, well, it's about 25 microarc seconds. It's amazing. And the black hole itself makes an angle of like 42 microarc seconds in the sky. We can also tell from this image that the supermassive black hole has 6,500 million times mass of that of our sun, and the size of its event horizon is like 20,000 million kilometers, which is bigger than our solar system. Is this an actual photograph? Not really. You see, we use optical lights to photograph something else, like this one or that one. We use optical lights. We see through optical lights. So yeah, definitely we do use optical lights. So in that sense, well, it's not a photograph. We used radio waves here, so it's not a photograph in traditional sense, at least. But wait, there's more to it, okay? It's more of a computer generated than a real one, because the distances between these telescopes, one is in South Pole. Just think about it, South Pole. So just because of these large distances, we get lots of gaps in between these photographs. Well, the supercomputer then analyzed these images and created an image using a predicted one. So we might say that it's not an actual photograph of a black hole. It's again computer generated, but just think about it, okay? Here I'm giving you parts of images of an object, and you have to guess which object this thing is. Can you guess? Yeah, you're right. I mean, that's an apple. Now, how did you say that? How can you tell me that this is an apple? You didn't have all those images, right? Still you say that it's an apple, right? Your brain did the same thing that supercomputer did there. So what really happened, your brain actually tries to look for patterns, known patterns to be exact. Well, so it knew how an apple really looks like. That's how it constructed the image that, well, it is an apple. That's why you just recognize that thing. So that's the thing. And same thing here, we can predict how a black hole can look like from the equations of Einstein. Well, so we knew, kind of like we really knew that how a black hole should look like, and it helped reconstructing that image, filling in those gaps. That's how this image is created. So as we knew from Einstein's prediction that how a black hole should look like, it helped us reconstructing the image and filling those gaps. As always, thanks for watching and stay curious. Happy knowledging.